So we started last time with section 5.1. We're taking a look at the natural logarithmic function, and specifically we're looking at differentiation. And I think that we finished through example C right here. That's our last thing. Is that what we did last thing? Excellent. Okay. So we looked at finding derivatives. We've looked at simplifying some of those derivatives that we've found. Sometimes they have this unexpected simplification that makes them a lot nicer. Again, on your gateway, you're not simplifying anything, but for these you would. And so moving forward from there, we're going to talk a little bit more about... So if we have a logarithm of an absolute value, right, like this one, if f of x is equal to the natural log of the absolute value of x, then the derivative retains the same form. Okay, so the absolute value will still give me a derivative that's 1 over x. It doesn't change the derivative. We don't keep an absolute value in it or anything. It's still just 1 over x. So when we see this one at play, you can kind of ignore the absolute values, is what this means, right? So if we have f of x equals the natural log of the absolute value of sine of x, what derivative rule besides the natural log one do you see present here that we're going to need to use? The chain rule. Yeah, I heard a couple people saying quietly. It's the chain rule. I have a sine function embedded inside of a log function. So when I'm working on the derivative with the sine rule, we take the derivative of the outside function, which is the 1 over piece. And it's 1 over the inside, sine x. And we don't do the absolute value. It's just 1 over sine x. And then we multiply that by the derivative of sine of x. So what is the derivative of sine of x? Cosine of x. And if you're rusty on those, you got a paper. I gave it to you, right? Use it until it becomes a little bit more familiar. Now, on a gateway, you'd stop right here, and it'd be done, and that'd be lovely. But there's absolutely no reason for us to stop right here for what we're doing right now. This is the cosine of x over the sine of x, and that has a simpler name. Do you remember what it is? That's cotangent of x. Okay, so we're going to simplify in as much as is reasonably possible in a problem, and this is a place that we would stop, and it makes sense to do so. So I'd like for you, I made it at the bottom there. Note, the sine of x must be in absolute values at the beginning of the problem, right? So when it starts out, it says natural log of absolute value of sine of x. It has to have those absolute values on there. Why? Do you remember what we did with logs last time, or what we talked about with logs? Yeah. So the domain for the log function is it has to have x values that are actually positive, or input values that are positive. So the values inside of the absolute value here, they have to give us out a positive value to take a natural log of them. That's why those absolute values are absolutely necessary here. They aren't always necessary in different cases, and we'll see places where we could leave them and it'd be fine, but we can also remove them because we just don't need them. Here, at the beginning of the problem, they're absolutely necessary when we describe this function. Okay, so taking a look then at number 7, we've got a little bit more in-depth function. It's not a scary one, but it's got a couple pieces to it anyway. So we have f of x is equal to 3x squared minus the natural log of x. And it wants us to find an equation of the tangent line to this curve through that point that's listed 1, 3. Okay? So we did this a lot in Calc 1, where you do a bunch of derivatives, and then you do one where it talks about tangent lines. The process is still the same here. So we're going to take the derivative. So first of all, what is the derivative of 3x squared? 6x, good. And then the derivative of the natural log of x? 1 over x, exactly, cool. And then what we're supposed to do is we're supposed to get, well, what this gives me, I should say, it gives me the slope of a line. But is the slope of a line arbitrary, right? I've got this x involved. The value of the slope will depend on the coordinate point that I'm at, and the point that they're giving me that I'm at is 1, 3. So I can find the slope at the point I care about by evaluating it at the x value I was given, which is the value of 1. So, oops. There we go, 1 in here. Oh, and I did it there too. Good grief, I got carried away. How about that? 6 times 1 minus 1 over 1. What does that give me? Yeah, that's 5. And then if you'll remember, when we find the tangent line, we just use the line equation that you learned back in like algebra 1. Y minus y1 equals m times x minus x1. The m value is what we just found, 5. The ordered pair, we were given the 1, 3. The x value is 1, and the y value is 3. And then again, we're going to clean this up and write it down as y equals. It's a friendlier version of the same thing. So I have 5x minus 5. I'm going to add my 3. And the equation of my line would be 5x minus 2. Yes?
In gateway, where would you start?
You wouldn't have this in a gateway. The gateway only asks you to find derivatives. Doesn't ask you to find tangent lines.
It is online.
No, it's in class. We'll do it in class on paper. Yeah, we're doing class on paper. Any questions on that one? Okay, so this isn't a gateway style question, but it is stuff that you're going to see on your homework, right? And potentially in quizzes or on tests. So part B to this one, if you flip over, we're going to flip back and forth for a little bit, asks us to use a calculator to graph the equation and to graph the tangent line. So if you have your calculator with you, grab it. If you don't, I will sketch what is on mine on the screen, and you can maybe look in on with a nearby classmate. So we're going to graph 3x squared minus the natural log of x. And I think I'm going to do it just in a way. I usually start with a standard window. Okay, so if you're familiar with your calculator, that's the negative 10 to 10 x's and y window. If you have a TI 83 or 84, you hit zoom 6 is the standard window. And it gives you what kind of looks like half of a parabola. That's what my graph looks like anyway. I'd like to look at it a little tighter though. I don't know if yours looks like mine. Hopefully it does more or less. Because it's hard to really tell what's happening near the y-axis. It's pretty clear that it doesn't seem to have any values on the left-hand side of the y-axis, and that should make sense because the x values need to be positive, right? Otherwise, I can't have a value for natural log of x. So they are going to be on the right side of the graph, but nearby the y-axis, it's hard to see what's happening. So I'm going to take my window, and I'm going to actually start at an x minimum of 0 and a y minimum of 0 to try and see if I can get a better idea. And that's pretty good. So it looks more like this. It's not actually hitting there. Maybe I should be more careful. I know it's not hitting on this axis, but it looks something like this. Does yours look something like this as well? If you zoom in and shift it around a little bit. Okay, great. So for those of you who are familiar with WebAssign, you know that what I'm about to say is the description, but for those of you who haven't done a lot with WebAssign, what will happen on a graph like this is usually they give you like 4 graphs and they tell you which one is it, they want you to pick which one is the mirror image of what you're looking at kind of on your own calculator. So this is our equation. And then in Y2, I'm going to go back, I'm going to put the equation we found on the previous page, 5x minus 2. And when I do that, I'll change colors on the screen. My graph actually looks very much like this. That's not very good, but let's try one more time. That's not too bad. It continues on after this line. Maybe I could shift it a little bit. Let me try one more time. There we go. That's a little bit better. The point where it crosses is 1, 3. That's kind of the whole argument that we had before. So here's 1 and here's 3. And there's a point right here where it actually intersects, give or take. So remember, that's what a tangent line is. Tangent line is a line that sort of just bounces off of the curve. It doesn't typically cross it. There are some exceptions to that based on the way the shapes of the curves are and so forth. But it typically bounces off of the curve, and this seems like a reasonable thing. So if we made an error in our equation, we might see it on a graph very quickly. Like we have 5x minus 2. If we had accidentally forgotten to do something, we got 5x plus 2, right? It's not going to look right. It's not going to look like it bounces off the curve there. And we would have a red flag that says, okay, I did something wrong. Something weird's happening. And we would go back and fix it. All right. We're going to use the derive feature of your calculator next to confirm our value. So this is more a reminder than anything. We've done this for those of you who took at least my class of Calc 1 and probably if you took Dr. Marsh from Calc 1, she showed you how to do this as well. So there's a function button in your calculator that's we call it the derive feature, and it says in derive when you pull it up like that. Okay, it's actually located under the math key. So if you click on math, and it's option number, I think it's 8. Yep, number 8. It pulls up like this, and it has a parenthesis after it. I think that's what it looks like in everybody's screen, no matter what version or what kind of type your calculator is looking at if you're in a TI 83 or 84. Now, there's two different things that can happen when you select this button. I'm going to show you what happens on my screen, which actually we need to be back in the regular screen to do this, and I messed all that up. Let me delete that again. Right here. So you're going to start in the regular screen, like where you would do like addition and subtraction or whatever calculations you would do. You're going to hit Math 8. Now, my screen actually pulls up a phrase that says this. It says in derive. Okay, so I'm going to show you what it looks like for me to write this down, and then I'll show you the other version. I would write down x, comma, y1, comma, and then the x value that I'm using is the x value of, I didn't write that right. They're backwards. y1, comma, x is what I meant to say, and then I have a value of 1. Okay, so in my screen, this is what I'm going to type. I'll show you where to find all those buttons if you're not sure where they are. In the other screen, somebody see it. Let me see it. What's yours? DDX. It pulls up a thing that looks like this. Has a parenthesis. Does it have a line after it? Mm-hmm. Line x equals, and then there's a box here. There's a box here. So it looks like that. Does everybody else's look like that? If you're using one of these, does it look like one of these versions? Okay, great. So those of you who have this version, you're going to end up putting y1 in here, and you're going to put an x over here, the 1 for x over here. Okay, so let me show you where we get y1, because everybody is usually pretty good with the other features. There's actually a comma on your screen right above the 7, if you're using the version that's the first one. So the location where I get the y1 is underneath the vars button. So if you go into vars, and then you go over to the Y vars. You choose option number 1, which says function. And then it's again option number 1 that says Y1. If you're using this type of calculator, have you all found Y1 at this point? Are you good? It's okay. Let me see.
It's been a while since I've used
It's
a
okay.
calculator for this specific thing.
Ooh, TI Inspire.
Yeah.
You're probably going to have to be on your own on that. I'm so sorry.
It's okay. I dealt with this all last year when I was going to do calc.
Use the user's manual. You'll be able to find it.
Yeah.
All right, so using this, or if you're typing it in the way mine is, which is how TI 83 is and some TI 84s, you're going to put a Y1, a comma. The X is on the screen, just like you would do in a graph. Put another comma, and then the number 1, okay? The point of this is that I want you to see that your technology is able to evaluate the slope at a particular point. And if you press enter at this point, it should give you the value 5. Does it? Oh. Does it give you a funny number? Mine did too. Mine says like 4.999, and then it goes some 7s in there, whatever, like that. Calculator's not perfect. Did you know? I got to tell this to my son at home again later, right? Now that he's able to use a calculator, like it's gold standard of things. Your calculator does not actually know how to take derivatives, believe it or not. What your calculator does is it does numerical approximation, and it makes errors when it does so. So this value that it's showing up here at does not look like it is exactly 5, but it is, okay? So we are getting the value of 5 to confirm this. I'd like to show you one other way to do this, just so that you're aware. It's not always perfect, but because we've already graphed it, I know it'll work. If you look back in your graph, okay, so my graph looked like that, like I drew on the screen over here, right? If I select, I don't remember where it is, second trace, option number 6, under second trace, says dy dx. Okay, dy dx is notation for derivative. So if you select number 6, it actually asks you at the bottom of the screen, you don't maybe know that it's asking, but it asks you for the x value. So if you hit the x value is equal to 1, it'll type it on the bottom of your screen, and you can press enter, and it will tell you the dy dx value on the screen. Now, I mentioned at the beginning, this is not always the best way to do it. The reason I know it would work here is because the image that we were seeing where the actual derivative at that point 1,3 was on, like where it was visible at this point. If it had been off screen, it would have given you an error. So it actually has to be within the window of the screen for this feature to work. But again, it works pretty nicely. And again, my calculator's struggling. I've got 4.9, I think I've got 6 9s and then a 7. Right? The calculator's numerically approximating. It is the number 5. The calculator just doesn't understand that. Okay? So today, and actually every day, you are smarter than your calculator. All right. Oh, man. I know those of you who took Calc 1 with me are going to be so excited to see this show up again. All right. So we're going to look back at implicit differentiation with a very real goal in mind. It's not just to torment you again. Okay? We need this for another piece that we're going to be doing after this in this section. But I want to remind you what implicit differentiation does. Now, there's more than one way to do implicit differentiation. I'm only going to teach it from one perspective. If you've learned it in a slightly different way and you're still getting the same answer that I am, then that's fine. You're welcome to do it in a different way. Okay? Everybody good with that? Okay. So the way that I talk about implicit differentiation is just like I talk about derivatives. But we're treating both x and y in the problem as needing to find derivatives of them. So when we see the first piece that says natural log xy and they're together, if I leave this as is, I have a chain rule because the xy is inside of the log, and I also have a product rule because the x is multiplied by the y. Everybody see that? Okay. We don't want to do it that way. We learned a property of logs that's very helpful for simplifying things. And if we remember it, it will make the derivative process easier a lot of the time. So if I remember that process, I can separate this to say that this is the natural log of x plus the natural log of y. I still have plus my 5x, and I still have it equal to 30. All those pieces stay the same. So the reason that that's so nice is because taking the derivative of the natural log of x is easy. The natural log of y is not bad. It's a little bit more complicated, but it's all much better than taking the derivative of a product. Okay? So that's more complicated. So what is the derivative of the natural log of x? 1 over x. What's the derivative, do you suppose, of the natural log of y? 1 over y. And then I need to remember that y is a variable of another function, so I have to do, several of you are saying it good, dy dx. Lovely. Plus, now what's the derivative of 5x? 5. And the derivative of 30? 0. Cannot tell you how many times people forget when they get to the 30 and they just write the 30 down. So keep your head on, right? Don't stop too quick. And then my goal is I want to solve it for dy dx. Now, the answer may have still y's in it. That's okay. It may not, but this one will. But I need to solve it for dy dx. So that means I need to get this piece right here alone. So either move it or move the other pieces. I'm going to move the other pieces and leave the dy dx on the left. So I'm going to move my 1 over x to the right-hand side. So I have negative 1 over x. And I'm going to move my 5. So I have minus 5. So this is 1 over y dy dx equals negative 1 over x minus 5. And then the last thing to do is to move the 1 over y over. Yes, I'm dividing by 1 over y, but that's not a real helpful way to write it. It'd be easier to write it as multiplication by y. So my dy dx will give me negative y over x minus 5y. I'm okay with you leaving it like that. You might see a version where it merges it back together with a common denominator. That's fine too. Doesn't bother me in the slightest if you want to do that. So if you merge it back with a common denominator, you're going to end up multiplying this like so. And you would end up with a single fraction that says negative y minus 5xy over x. It's not any better. It's also not any worse. So either of those versions, I'll take the blue away so that we can see how it was written originally. That's not what I meant to do, but that's okay. 5y, right? Okay. So either of these versions of the derivative are fine. There's no implicit differentiation on the gateway either. So this is not present on the gateway. Okay, any questions about those two or that process? Because we're about to use it for something else. Okay. So here's what we're going to be using it for. What we're about to do is something called logarithmic differentiation. Now, if you just got this derivative, and I said, find the derivative, you would not be happy with me, first of all, right? This looks terrible. I've got quotient, I've got products, and I've got chain rules, all inside the problem. The only thing I don't have, maybe that we've discussed, is like, there's no logs. Or there's no logs inside of here, but that's about it. Everything else is there. This is an awful looking problem. So watch what we can do instead. Are you ready? We're going to take logs of both sides. I know that feels a little funny, but just walk through with me and you'll see why. So now I have the natural log of y. But over here, I have the natural log of all of this stuff that has multiplication and division in it. And I can separate logs when they have interiors that have multiplication and division. Or I can make them separate log expressions. So I can rewrite this to say natural log of x squared plus the natural log of the square root of 3x minus 2. We're going to simplify more in a minute. So if you're looking at this and saying, why is she doing more? We will. And then minus the natural log of x plus 1 squared. That is leaps and bounds easier already. Now, we're going to have to fix the fact that we just threw a natural log in there and it wasn't there to begin with. We're going to have to compensate for that. But the compensation is not going to be a big deal. It's an easy compensation for the value that this is, okay? So we can do one more feature. Each one of these has actually got a power involved on the whole expression, right? So natural log of x squared can be rewritten as 2 natural log of x. And the natural log of the square root of 3x minus 2 can be rewritten as 1/2, because that's the same thing as the square root, the natural log of 3x minus 2. And the natural log of the x plus 1 squared can be rewritten as 2 times the natural log of x plus 1. Please consider what you can't do. You can't separate anything with addition and subtraction inside of logs. So there isn't any way to separate these any further. They are as separated as they can be, okay? But they're also in a form that makes taking the derivative of them now pretty friendly. Now we took a derivative a moment ago of the natural log of y. What's the derivative of the natural log of y? 1 over y and dy dx. Okay. What's the derivative of 2 natural log x? 2 over x, or you can do 2 times 1 over x if you prefer. How about the next one? So there's a 1/2 here. What is the derivative of the natural log of 3x minus 2? 1 over 3x minus 2 times 3. Very good. So we have a chain rule there. It's not a terrible one, but we do have one. Right, derivative of the outside, derivative of the inside. And then the next one, the derivative of the natural log of x plus 1 would be 1 over x plus 1. I'm going to go ahead and put the 2 on top. If you don't want to and you put it in front, that's fine. What's the derivative of x plus 1? It's just 1. So it kind of looks like I'm not doing a derivative of the inside, but I am. If you want to see it, just put times 1 to remind yourself later. We did consider the probability or the problem there. Okay, so just like in this problem over here, I need dy dx alone on the left. So I'm going to have to move it back over, the y that's over here to the right. Okay, I do have to shift it back. Everybody good so far? Okay, so I'm going to multiply by the y. So this is dy dx. Now, you won't have logarithmic differentiation on your test. So what I'm about to do makes sense in terms of what we're doing in general, because we're always going to be simplifying a problem like this. So we're going to clean up the things on the right, and we're going to be multiplying them by y we're going to do both of those things. I'm going to kind of do it in the same step. So I have a 2 over x here, plus, this is a 3 over, and I'm going to leave this as 2 times 3x minus 2 for now. And then I have minus the 2 over x plus 1. And all of this is now going to be multiplied by y. Now, I mean, we're going to simplify this into a single fraction. We are going to do that. But the bigger issue on this problem is that I'm not going to leave this question, leave the answer to this question with a y on the right. And the reason I'm not is because I know what y is. It was the original thing I was given. The original equation I was given said y equals this mess. So I'm going to take the mess and I'm going to put it in for y. That's not real great. I understand that. But it's better than the derivative that we were faced with at the beginning when we were looking at it. So let's actually get some common denominators to start with, and then we'll deal with the y situation second. I think I'm going to have to switch screens because I think I'm out of space. Yep, I have more space. Okay, so I think this will be my last step on the screen, and then I'll copy and paste a couple things. So to get these to have common denominators, I need all the pieces of each denominator that are not present. So I'm going to need a 2 here. I'm going to need a 3x minus 2 here. And I'm going to need, you know what, let me do it this way. Take it back. A 3 here, a 3x, sorry, minus 2 here, and an x plus 1. And I'm going to have that same expression on bottom. Okay, there it is. The second fraction is missing the original x, and it's missing the x plus 1 from the end. And then the last expression is missing the x from the beginning and the 3x, the 2 in the middle, and the 3x minus 2 in the middle. So x, 2, and 3x minus 2. So it has been said before, in fact, I said it this weekend to somebody else, you don't get really good at algebra until you get to calculus, because we use it all the time. This is one of those times when we're going to use it, and we're going to clean things up. So we probably should multiply 3x plus 1 and x plus 1, 3x minus 2 and x plus 1 out. So I'm going to get, that would be 3x squared, and then I have positive x and minus 2. Does that look right? Is that okay? I'm going to multiply those together. I had to multiply them by another 3 and a 2 at the beginning. So I'm going to multiply through that with 6. So I'm going to get 18x squared plus 6x minus 12. And then the denominator is going to be much the same, but I actually don't want to multiply the denominator out because it's going to cancel with some stuff in a little bit. So we're going to leave the denominator factored. That's a very common trait when we work with these, is to get the common denominator, leave it in factored form. We have to clean up the numerators to see if they combine. So our denominator, we'll write it here in a minute. The numerator for the second one is much better. I just have to do 3x times x plus 1, so that's plus 3x squared plus 3x. And then on the last one, I have 2 times 2 is 4x. So 4x times 3x, and the negative at the beginning is negative 12x squared. And then I have that same negative 4x times negative 2, so I have positive 8x, I think. And then our denominator is going to be the 3 and the x. I don't know why those are 3s. They should have been 2s. Jiminy Cricket, that's terrible. All right. These should have had 2s here. That's what happens when you zoom in and zoom out too many times. We'll fix that first piece right here. Okay, should have multiplied 3 by 4. Try again. So we need 4 multiplied through that. So I have 12x squared. plus 4x minus 8. I think that's right now. What do you think? Okay. All right. Denominator, I don't have 3 anymore. I didn't have 3 to begin with. I just wrote it down wrong. I have a 2 and I have an x. I have a 3x minus 2 and I have an x plus 1. And all of this is being multiplied by the y value, which I will plug in on the next screen. Okay, so the y that I was working with before, we'll consolidate the numerator and then we'll put the y in. Oh, that's good. Look at that. 12x squared and negative 12x squared. I like that. There's a 3x squared on top still, right? I have, so take care of that one. 7x plus the 8x of 15x, right? 15x. So that took care of this one, and that one. Is it just minus 8 left? I think so. Wow, that's so much better than it was before, isn't it? 3x minus 2, x plus 1. All right, we're going to put in what y is. So y, as it was originally given to me, is x squared times the square root of 3x minus 2 over x plus 1 squared. And you'll notice the original problem actually gave a condition. It said that x has to be greater than 2/3. That was necessary. Otherwise, we couldn't have done the logs and made sense of it. So we don't have to actually do anything with it, but just understand there is a reason that they gave you that stipulation. Okay, so I was talking about here at the beginning where it says x is greater than 2/3. Okay. All right, does everything else look okay from what I've got written down? Miss any pieces or anything? Okay, so notice a couple things. This x plus 1 and this x plus 1 are the same and they're multiplied, so I can just take that and make it a power 3, right? Okay, so that's good. And the other thing you can notice is that this denominator piece right here and this piece right here are also similar, right? I've got a square root of it in the numerator and I've got the whole value of it in the denominator. So you might remember from trig how that could have come about. You can also remember it from an algebra course on powers. It's a power of 1/2 on top. It's a power of 1 on bottom. So properties of exponents say that I can combine them with subtraction. Since there's more on bottom, I'm going to keep it on bottom. So if I take 1 as an exponent minus a 1/2, I get a 1/2, but it's on bottom. So the pieces that I have right now, I'm still going to have the 3x squared on top, the 15x on top, and the negative 8 on top. I'll deal with the other parts in a minute. I'm going to have a square root of 3x minus 2 on bottom now, and I'm going to have an x plus 1 cubed on bottom now. It's not good. Let's try it again. There. The one other thing that you might notice is that there's an x here that can cancel with one of these x's here. So that will leave me with an additional x on top. I'll multiply that through in a minute, and a 2 on bottom. I don't have all evens on top, so I can't simplify that one. But the only other thing I can do then is distribute that x through. So it's 3x cubed plus 15x squared minus 8x over 2 times the square root of 3x minus 2 times x plus 1. So without question, when you see logarithmic differentiation, depending on how messy the thing is, and this one was really messy, did that on purpose, right? This is going to be one of the longer style problems that you're doing. It is, understandably so. And you'll want to take some care and make sure that you're paying attention and being careful, because I missed something along the way because I was zooming in and zooming out, so that you don't end up being off at the end. Okay, any questions on that? All right.